Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I really appreciate you tuning in. In this video, I'll walk you through a basic Blimp script and illustrate some of the major commands and keywords. As you'll see, it's simple to estimate even complicated models in Blimp, and you don't need deep knowledge about estimation or missing data handling to use the software. Before we get started, I want to acknowledge the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp at the same homepage. So let's jump in and take a look. To provide a context, consider an educational intervention targeting math achievement. The multiple regression model shown here features three predictors: a dummy variable coding to experimental conditions, math self-efficacy, and pretest achievement scores. In the path diagram, straight arrows denote regression coefficients, and the curved arrows reflect associations among the predictors. Self-efficacy and the post-test scores have missing data. A typical Blimp script consists of commands ending in a colon and keywords and subcommands that end in semicolons. I use a mixture of caps and lowercase to differentiate commands here, but Blimp isn't case sensitive. The color coding also mimics what you'll see in the Blimp Studio interface. Roughly speaking, a Blimp script consists of three sections. The first section describes the data and variables. The second section describes details about the fitted models. And the final section specifies computational details. To start, let's see how to read data into Blimp and specify features of our variables. The data command specifies the location of the input data set. The data should be a space or comma delimited text file. Because I'm not specifying a file path, Blimp automatically looks for the input data in the same folder as the Blimp script. Next, the variables command specifies the names and the order of the variables in the input data set. If the data file has the variable names as column headers, you would simply omit this command. The ordinal and nominal commands define categorical variables in the model. Binary variables like experimental condition can be defined as ordinal or nominal as the underlying statistical model is identical. Although not shown here, there's also a count command that invokes a negative binomial distribution. Finally, the missing command defines the numeric missing value code in the data. Blimp requires every variable to have the same missing value code. The next group of commands specifies features about the analysis model. Let me walk you through this section of the script. Usually, it's a good idea to avoid estimating unnecessary imputation models for complete variables, as that simplifies estimation and speeds up convergence. Listing complete variables on the fixed command takes care of this. Next, the center command applies grand mean centering to a pair of predictors. Group mean centering is also available for multi-level models. Finally, the model command includes one or more regression equations. Each equation in the model section consists of an outcome variable to the left of a tilde and predictors to the right. The tilde is essentially like an equal sign in a regression equation. Note that the model command I'm using here invokes Blimp's default factored regression specification that splits the multivariate distribution of the variables into a univariate model for the outcome and a multivariate normal model for the predictors. I described this specification in the Blimp modeling framework video. Next, I want to show you a couple different ways to expand the model statement. Blimp's modeling framework is unique because it lets you have mathematical functions on the right side of a regression equation. Models with interaction effects are a common example. The path diagram here shows moderated regression model where the experimental condition moderates the influence of self-efficacy. The product term for this model is specified by joining two predictors with an asterisk. Importantly, that product isn't a variable in the model, but rather a function of two other variables, either of which could be incomplete. As a second example, suppose the self-efficacy scale is the sum of 5 items, any of which could have missing values. Summing the questionnaire items inside parentheses invokes a missing data handling procedure that imputes the individual questionnaire items while simultaneously preserving the sum score as a predictor in the focal regression. The model statement can also include more than one regression equation. Essentially, we can estimate path or structural equation models. This example shows a mediation model where the experimental condition and pretest scores influence self-efficacy, and all three variables in turn affect the outcome. In models with multiple equations, Blimp creates a separate output table for each dependent variable. By default, these tables are listed in alphabetical order. In some situations, we may want to reorder the tables or group sets of tables together. In this example, I use labels ending in colons to reorder the two tables so that math post-test results appear first on the output. This functionality is especially convenient for latent variable models where you might want to group measurement and structural parameters together on the output. Next, I want to show you how to attach labels to parameters and illustrate a few applications of that functionality. Among other things, you can use labels to impose equality constraints, compute additional parameters that are functions of the estimated parameters, and specify custom significance tests. In this example, I use the @ symbol to name a pair of regression coefficients A path and B path. I use these labels to reference the two slopes in subsequent commands. For example, here I use the parameters command to define a new slope coefficient called indirect that equals the product of the two mediated pathways. This new parameter has a distribution that naturally varies as a function of its component pathways. Another way you can use labels is to construct custom significance tests. In this example, I label the three slopes in a multiple regression model and use the test command to invoke a walled chi-square test. The first test command evaluates whether a single slope equals 0, and the second test command evaluates a pair of slopes at the null value. Blimp's computational engine uses the Bayesian framework and Markov chain Monte Carlo or MCMC algorithms. Let's take a look at how to specify computational features and modify the MCMC algorithm. Broadly speaking, MCMC consists of two major steps. First, Blimp estimates a series of regression models using the filled-in data, then it uses the resulting model parameters to construct distributions of imputations. These two steps are repeated thousands of times. By default, Blimp invokes two MCMC processes or chains from different starting values. We need to divide the MCMC chains into two segments. The first segment is a warm-up or burn-in phase that allows the algorithm to converge to parameter values that are optimal for the data. The estimates from the burn-in phase are discarded. The second segment is the analysis phase that generates the parameter values that we use for inference. Taking a look at the Blimp syntax, the burn command specifies the number of warm-up or burn-in cycles completed by both chains. The iteration command specifies the number of parameter estimates for the final analysis, with the number of requested estimates distributed equally across chains. Finally, MCMC estimation relies heavily on Monte Carlo computer simulation, and the integer value after the seed command initializes the random number generator so it produces the same results every time we run the script. Blimp produces summary tables for every fitted regression model, and you can use those tables to form conclusions about your research questions. Because the imputations are updated at every computational cycle, the resulting parameter estimates average over many realizations of the missing data. However, if you want to save a subset of those imputations for a multiple imputation analysis, that's also possible. In this example, I use the nimps command to create 20 filled-in data sets, and I use the chains command to specify a unique MCMC process for each. This setup saves the filled-in data from the final iteration of each MCMC process, which ensures that the imputations aren't autocorrelated. Finally, the save command specifies the format and file name for the imputed data. The stacked format shown here appends the 20 data sets to the same file, which I name imps.dat. Because I'm not using a file path, the imputations are saved to the same folder as the Blimp script. Imputations can be saved in different formats. In this example, I specify a stacked format that adds the original incomplete dataset to the top of the file. This format is required to analyze the data in STATA, for example. Finally, this version of the save command writes each imputed dataset to a separate file. The asterisk in the file name gets replaced by an integer, which in this example ranges from 1 to 20. This format is required to analyze imputed data in MPLUS, for example. Blimp also creates the necessary text file containing the names of the filled-in data sets. Now that we've dissected a prototypical Blimp script, let's see how to run the script in the Blimp Studio interface. To run a script, you simply click on the blue arrow icon on the toolbar. Running a script creates a paned windowing interface that contains the script, the output, and potentially trace plots. I walk you through the Blimp Studio interface in a different video. That concludes a brief tour of the Blimp scripting language. The video only scratches the surface of what's possible in Blimp. A detailed user guide with dozens of data analysis examples is available by choosing the Help option from the Help pull-down menu. Thanks again for tuning in, and I hope to see you in future videos.